Welcome back to this course on textile finishing. Let us first understand and revise what did we do till now. So, what we have learned is that the N-methylol compounds can be cross-linked with cellulose, that is the hydroxyl group of cellulose, via an acid catalyzed mechanism. So, we can either have a Bronsted acids where the proton is available for reaction, or we can have a pure Lewis acid mechanism where metal salts, the metal will actually act as a Lewis acid and it will be catalyzed. The other thing which we also have learned is that there is a synergistic effect. If metal salts are available along with a carboxylic acid, basically an acid which is hydroxy acid, all right. For example, acetic acid will not work, but citric acid, glycolic acid are good examples of the hydroxy acid, which should be the either alpha hydroxy or beta hydroxy. We also discussed about another class of catalyst called the phase separation catalyst, in which we have various ways in which the precipitation can occur. One of the phase can be separated, and in these types of catalyst, as the concentration of the solution increases, one of them which is less acidic and which has low solubility product precipitates, and once it precipitates, the pH decreases further rapidly, and so as the phase separates, the pH becomes more acidic, and so the catalysis can then become more effective. The other class of catalyst that we discussed was self-limiting catalysts. That is, they would evaporate as the curing takes place, and you may not have to wash the fabric because nothing may be left, but that is just the catalyst part of it. If the monomer or the cross-linking agent does not react fully, then you will have to obviously wash. One of the examples, for example, is hydroxy methane sulfonic acid, right. The other type of catalyst that we discussed in this class was self-neutralizing catalyst. One of the example was the basic aluminum chloride or aluminum chlorohydroxide. They are excellent buffers. So, the metal salt obviously acts as the Lewis acid and does all the catalytic activity, but because of the hydroxy groups present in this whole structure, it remains more or less buffered and does not damage the fabric. So, this is what we learned about the catalysis last time. Now, we shall spend some time on cross-linking agents which are other than the N-methylol cross-linking agents. After all, what you required was there should be at least two functional groups attached, so that a cross-link can be formed. When we mean this cross-link, we are meaning covalent cross-links can be formed. So, they will remain more permanent and the same mechanism of crease recovery can be established. So, in the earlier lessons that we have discussed, so we had nitrogenous urea based cross-linking agents, DMU if you remember. This is the structure. Right, remember this structure. DMU was a cyclic urea, which had a structure like this. So, it is a cyclic urea with the same N-methylol structure, and in the DMDH EU we have 2 more hydroxyl groups attached. In this original cyclic structure. Essentially all of them are N-methylol compounds. So, these were 3 important, otherwise we could have many more number of N-methylol compound based on melamine and derivatives of some of these cyclic compounds, including DMPU or derivatives of DMPU. So, there can be many such number of cross-link agents, but what we remember is this is the group which we are interested in, which actually reacts at a suitable temperature and for if kept for a certain suitable time. Today we will look into another possibility where the N-methylol group is not the functional group. So, other possible cross-linking agents. So, one is a non-urea based nitrogenous. So, they may have nitrogen as one of the key elements, but they would not be urea based. For example, azidinyl group based compounds, isocyanates, pyridinium salts, they have nitrogen, okay? They have nitrogen, but they are not urea. We can also look into other group of chemicals which can be used as cross-linking agent, which are non-nitrogenous. Okay. If you just look simple compound like a formaldehyde itself, which also does not have any nitrogen, and theoretically the N-methylol compounds were formed by formaldehyde itself, and therefore, it is possible to react simply with formaldehyde also. Whether you do it or not is a separate story, but it can be done. Epoxy compounds, which are basically compounds based on this group. So, epoxy compounds, vinyl sulfones, you probably remember the reactive dyes based on vinyl sulfone groups. So, a vinyl sulfone can also be reactive group. Acid chlorides can also be used, which do not have any nitrogen in them. In addition, 2 more classes of compounds actually have been quite commercially successful and being recommended for cross-linking purposes. One of them is based on glyoxal, the others are carboxylic acids. So, today we shall discuss little bit about these cross-linking agents and how they can be reacted with cotton. So, let us first talk about nitrogenous, but non-urea based cross-linking agents. Interesting compound which we know as aziridinyl compounds, or sometimes also known as epimines. Okay? Epimines. So, epimine basically, or aziridine, this is the group that we are looking at, a cyclic group which is NCH2CH2, cyclic compound. Now, cyclic compounds are reactive, and theoretically you can form a link of this type, that you have this compound, any compound, and then cellulose hydroxyl group is available, and in acidic medium a reaction of this type of a link, cross link, is possible. Now, why these compounds are more reactive? So, you may have been taught sometimes about this bare strain theory. So, what is this theory? It says that any deviation from normal bond angles. What is a normal bond angle? So, any element like a carbon, for example, forms 4 bonds. If you remember, you can make 4 covalent bonds in a tetrahedral kind of a structure, and the bond angle is 109 degrees 28 minutes, right. This is the angle that normally carbon would like to form bonds. Like a methane, for example, all the CH groups will be having this angle. So, that is the bond angle. So, there are two things, one is called a bond angle, the other is called a bond length, all right. So, they are all fixed thermodynamically based on the possible structure. So, every element would have its own bond angle if they are making more than one bonds, at least more than 2 bonds. So, any deviation that happens from the normal bond angle for whatever reason would put strain on the bond. The bond would like to remain like this and you want to bend it, change the angle. So, the moment you change the angle, there is a strain which leads to instability of the bond. If there is no strain, this is the most stable structure thermodynamically. This is the position that the atom or atoms would like to have. But for various reasons, like I make a cyclic structure because I need it, and there must be methods which can make sure that I get a cyclic structure. In that case, those bonds are strained. For example, a 3-membered ring structure like the way we were talking about, aziridinyl structure or epimine, is a strained structure. So, these bonds are strained. If you have any strain, obviously, this is the one which will result into some instability, all right. So, a 3-membered ring would be stable or unstable. It will be relatively less stable. We should not say unstable, it will be less stable, or in the other way it will be more reactive. So, we talk about a 4-membered ring, a 5-membered ring, a 6-membered cyclic. If we have cyclic structures, Obviously, if we can say the 3-membered will be more reactive than the 4-membered, than the 5-membered, than the 6-membered. Now, a 6-membered ring also is strained, but the strain could be less if the configuration and conformation changes. For example, a 6-membered rings can form depending upon the chemical, either a chair form or a boat form, to make them more stable. If a 6-membered ring is planar structure, it will be in a way less stable. If the same structure is able to form a chair or a boat form, can take up, assume, will become more stable. Similarly, you are also aware that a single bond, a carbon carbon single bond versus a carbon double bond and a carbon carbon triple bond, the triple bonds will be less stable than double, and then double bond will be less stable than single bond, and what it therefore means is the reactivity of the double bonded structures or triple bonded structures is going to be high, and that is what is the reason that these type of chemicals can become more reactive, and what it also means is that maybe you can react at a lower temperature. So, in this compound, in these compounds that we are talking, there is a functional group, as we talked about, is a 3-membered structure. So, is more reactive, and therefore, the reaction can take place by opening of the ring. Let us say we have a compound So, in the first step you will have ring opening, and after the ring opening, finally you would get a structure if we are reacting with cellulose, something like this. So, ring opens from here, this portion becomes free, and then it can react with cellulose. Remember, is there any loss of any element here? No, and therefore, this reaction is in some sense we can call it an addition reaction. Okay. So, reaction with cellulose is what we saw, that will make an ether link. So, you make an ether link. So, if you have to make a cross link, then what will happen? Then you will have to have a structure which is of this type, a bifunctional agent, and this can react with cellulose on both ends, for example, both two hydroxyl groups of two different molecules, and can form a cross link, first by ring opening and then reaction. Reaction would be generally in acidic medium. Now, this question, if somebody asks, can they react with wool and silk? Yes, they can react with wool and silk, again by ring opening with the amines, and therefore, if someone is interested in developing cross links in protein fiber fabrics, you should be able to use them quite easily. So, if we look at compound like this, the cellulose, one of the compounds could be carbonyl bis aziridine. So, you have a carbonyl compound, simple compound, can react finally with cellulose by opening, and you can make cross links. So, I hope you will be able to write the cross linking reaction by opening these rings on two sides. The other compound also is there, which is an interesting compound again, which is based on a phosphine oxide. It is a tri-membered, you can not the tri-membered, 3 aziridinyl groups, because there is a tris there. So, these type of compounds have been suggested to be used for cross linking purposes. You can appreciate that a bifunctional agent definitely will give a cross link and will be more flexible. A compound like this will give you possibly little more stiffer thing, but interestingly it also will introduce phosphorus into the structure, which we will learn later can be a good flame retardant. The other compounds that we are looking at are isocyanates. If you have bifunctional isocyanates, then you can obviously take them as a cross linking agent. What is an isocyanate? This is the kind of structure that you see in an isocyanate. All right. Have you heard about this isocyanate? These are very highly reactive systems, and if you have any memory or if you have heard about the Bhopal gas tragedy, where isocyanates were the ones which were being used there, and they react very quickly with water. So, bifunctional compounds can react with cross linking agents. The reaction with water could be can give you a carboxylic group. This reaction with water, is it an addition reaction or a substitution reaction? This reaction also is an addition reaction. What type of a link does it form with, let us say, instead of this, if we had cellulose this will be able to form a link So, this link which contains N C O double bond and O is also known as carbamate. Or also urethane. You heard quite a lot about polyurethanes. So, you would require some compounds which can react like this. So, it reacts very much with water itself. The one thing you can be quite sure is you will not be able to do any cross linking reaction in water medium, right, and the reaction is instantaneous. It is room temperature and could be very exothermic, and therefore, you may have to do this reaction with cellulose or any other such material that you want to do in through a solvent medium, where the reaction will not take place with the monomer till the time the other compound like the cellulose hydroxyl groups or an alcohol actually or an amine is brought. So, they can also actually link with amines, that means primary amines or any other amine which are available, let us say, in wool and silk fibers. So, you can see it is possible to do cross linking within the intermolecular spaces of wool and silk as well. So, the thing that we have to remember is there can be only bifunctional agents which can react with compounds like this, all right. So, you can just have simple compounds of various types which can be generated, synthesized. R could be anything, and you will be able to do a cross linking. Can you write the cross linking reaction with cellulose if you have a compound like this? I am sure you can do it yourself. Another nitrogen based compound is pyridine, not very popular these days, but it is a very interesting compound as such, which has got a nitrogen in the 6 membered ring. So, sometimes it can be written also as NC2 NC5H5, right. But this is not so much soluble in water. Benzene also is not soluble, toluene also is not water soluble. So, this also compound is not water soluble, but if you make salts, then it becomes water soluble. For example, the H, if it is added here, it takes a positive charge, the nitrogen, and then you have, let us say, a chloride ion. So, you can have salts of pyridine which can be used for cross linking purposes. The pyridine salts are interesting compounds. Let us see what kind of interest that it can generate. So, first of all, one must remember that if you have a dipyridinium salt, then they can work as cross links. They react as chlor-alkyl compounds, chlor-alkyl compounds. For example, this is an interesting compound. This is the pyridinium salt C5H5N plus and minus. It has reacted with any other compound, for example, an RCONH, an amide kind of a compound, which is reacted in this manner through a thing. So, the reactive group is here now. If you put, let us say, cellulose, which we have been representing as cell OH, and you heat during this process, what will be there is an HCl will come out, HCl will come out, and plus pyridine will come out. So, HCl and pyridine will come out when we heat, and so what you will get is some structure of this type. So, a reaction can happen and you will get a link with cellulose. They react as if they are chloralkyl compounds, like there is a chlorine which is going to get replaced and pyridine gets separated, which obviously one has to take care that it is not very easily mixed with the drain water or any other things, and it should be carefully taken away. Because HCl is going to be evolved, so mild basic conditions are going to be good, so that the HCl becomes during the reaction as a sodium salt or some such thing, so that it is neutralized. So, one of the interesting compounds is a compound which has got a large alkyl group and an amide also, an amide which is also linked with another CH2 group, and then you have two such groups present here, which by the same mechanism as we have discussed before can react and form a cross link, right. But interestingly, if you have groups like this also attached, people were interested in this kind of compound, then you can get water repellency, which we will talk about later. Okay, so what have we learned today? We have learned there is a very interesting relationship between the reactivity and the cyclic nature of a group, which is explained by the Baer strain theory. So, if you have a 3-membered ring, it is going to be more reactive compared to a 4-membered ring, compared to a 5-membered ring, and then the 6-membered ring. So, reactivity can change because there is a strain on the bonds. Then we have also learned today that the cross-linking of cellulosic fabrics can be done by using non-urea based nitrogenous compounds like Aziridine compounds, isocyanates, and pyridinium salts. Okay. And remember, all these are non-urea based nitrogenous compounds. All right. So, we stop here, and in the next class we shall consider non-nitrogenous compound that also can be used for cross-linking purposes. Okay? Thank you.